Welcome to part 3 of the particle physics slideshow that I'm recording to go with my lessons on the AQA Particle Physics specification for A-level. Just to review where we're up to so far. So we started by looking back at the GCSE knowledge you have on the structure of the atom and also the basic decays alpha, beta and gamma. We then looked at specific charge. Now this is a critical, simple thing that you must be able to calculate for different species. And we don't have time to practice it lots. It's a simple formula with just 3 items in it. But lots of students find it difficult because they don't practice it. They don't go away and think about the notes that are given. So if you're not sure on those things that I've mentioned, please do go back and watch the earlier videos, make some notes, do some practice questions, maybe use physicsandmathstutor.com or go to the past paper questions on the AQA website. It's vital that we get this right as you move along. There isn't time at the end to practice everything. Now, one of the things I tried to do in section 2 was to introduce the beautiful symmetry of what we call the standard model. So far I've introduced 2 classes of particles, the quarks, which come in pairs like the up and the down, and there are 3 generations of them, so 6 quarks in total, of which AQA A-level physics looks at 3, the up, the down and the strange. But the symmetry is there with that 3 generations of pairs of particles, with further symmetry that there is an anti-up and an anti-down, so where the up is charge plus 2/3, as seen in the formula sheet section shown on the right of the slide, the anti-up must be minus 2/3 charge and minus 1/3 baryon number. The other class of particles we looked at are the leptons, and again we get these 6, and this time we look at 4. Now a name I haven't used much yet is hadrons. Hadrons are all those particles made up of quarks. And for reasons that we may discuss in class, we never find quarks on their own. They come in 3s, and you'll be thinking hopefully, oh, I know that. They're called baryons. And you'll notice if I put 3 quarks together, we get a baryon number of 1. Or they come in pairs as a quark-antiquark pair. And you'll be thinking, I know that too. They're called mesons. And mesons have a baryon number of 0 because a +3rd and a -3rd. So it's really critical that you're aware of those words we've used so far and you start to practice them. And we add a new one in now. The hadrons are that class of particles made up of quarks. So the next place we want to go, and I remind you this is just a cut from the syllabus, so you can go and have a look at this on the AQA website. It talks about the weak interaction. Now I've said very little about the interaction so far, but you will recognise beta minus decay. Beta minus particles came up at GCSE, and we've revisited that slightly and added in the anti-neutrino to a beta decay. And the experimental basis for this is that beta particles come off with a varying amount of kinetic energy. And for energy to be conserved in the decay, there must therefore be a 3rd particle. And this is the anti-neutrino. Well, it turns out that there is a reflection of that decay called the beta positive decay. And a beta positive is a positron, just like a beta negative is an electron. So the beta positive is the antiparticle of the beta negative. And so it won't be entirely surprising to note that when we get a beta positive decay, we get a neutrino. So beta minus, an electron and an anti-neutrino, beta plus, a positron, which is the proper name for an anti-electron, and a neutrino. But there's another decay, electron capture, which follows exactly the same pattern, even though its name is slightly different. In fact, its name is very helpful. A proton captures an electron. And electron-proton collisions. Now, I'm not going to talk about those today, and we'll leave those for the end of the course, because they don't quite fit the same pattern. W plus and W minus as the exchange particles. Well, we haven't talked about exchange particles yet, and therefore that's something I need to introduce today. Now the spec also requires that you can draw simple diagrams, draw and interpret simple diagrams to represent the reactions above in terms of incoming and outgoing particles and exchange particles. So a very quick reminder. You did beta decay or beta minus decay on the GCSE spec. A neutron changes into a proton, and we've now covered the fact that that's because a down quark changes into an up quark. The beta particle, the electron, is ejected from the nucleus instantaneously, as is the antineutrino. The story of the neutrino is something that we'll discuss in class, but if you are interested, there are many interesting websites and podcasts that you can listen to about that discovery. Now, a quick health warning. The A-level examiners use this as a quick check as to whether you've actually progressed. So if you write a beta decay without a neutrino, they will certainly penalise that. Now, that piece of knowledge, carbon-14 turns to nitrogen-14, we could look at different levels of abstraction. So we could say, well, actually, the 6 protons nothing happens to, and 7 of the neutrons nothing happens to, because carbon had 8 and 7 of them remain. So we've talked about, and you could recognize the fact that really in all of that, all that's happening is a neutron turns into a proton, and we call that the nucleon view. Nucleons being one of those words we introduced, a group term for protons and neutrons, particles in the nucleus. But we could think about it on a quark level too. Up, down, down turns to up, up, down. So we could say that the first up, well, nothing changed just there, that remained. And the last down, nothing changed there either. That just stayed the same. So what really happened was a down turned into an up. They're all correct views of this decay, and picking the most useful one to explain whatever question you're trying to explain is a skill for A-level. Now, beta positive decay requires very little extra teaching. A proton turns into a neutron, a positron. So all other particles, their antiparticle, we just prefix anti. So an antiproton, an antineutron. We don't do that for the electron. Although we could say an anti-electron, we almost always say a positron. Okay, and so when we get an antiparticle in the beta, we get a real neutrino, and we will talk about why that is the case later. I think I pointed out right near the start of section 1, it's very difficult to know which bits to talk about first in this syllabus. There is so much new material, and therefore it's really important that you'll just know that you have to wait for certain bits of information. So the reason why one comes as an antiparticle and one comes as a real in terms of the beta and the neutrino is one you're just going to have to hold out for. Now, you should definitely be pausing at this point and making some notes. You need to know this. Right? Being aware of it and comfortable with it when written on the screen simply isn't enough. You need to be able to pull at that knowledge quickly, write it down in an exam. So you should have some notes. Maybe you've downloaded the cram revision cards that I might have mentioned in class. If I've forgotten to mention them, then ask me in class. But this has got to be knowledge that becomes comfortable, like your times tables. Now, those two beta decays, beta plus and minus, are the workhorse of year 12 questions on particle physics. So we need to also cover the electron capture. Older textbooks would call that K capture. And we need to look at those collisions that I said we were leaving for today. Okay. But the beta decay is the workhorse. If you are not confident with that decay, you will drop significant numbers of marks, both on the multiple choice and on the written questions. Please do go back, make some notes. The reason we do these videos is so that you can practice in class. Class isn't the time for me to re-explain or basic knowledge. Okay, so the next part of the spec I want to look at, and I would suggest you pause the video here, is what's described as the interaction. So we've done enough particles now that we can start thinking about the way they interact with each other. Okay, and that bit at the start, the four fundamental interactions of gravity, electromagnetic, weak and strong, we also call those four fundamental interactions the forces. Okay, and lots of theoretical and experimental physics in universities and research institutes today is based on trying to combine those forces. And there were early successes. So Maxwell combined the electric and the magnetic forces with his electromagnetic equations that you may wish to go out and read a little bit about. So what we see is early on in our understanding as humans of the physical world, we find lots of forces, and as we move forwards, we start to realize that many of them are manifestations of the same underlying physics. And we hope one day to find one bit of underlying physics that explains all of those forces. Whether that's the case or not, we don't know. If we knew, then that line of physics would be over. Science is about the unknown, not about the known. What we're doing with you here is moving you towards the boundary where that unknown exists. So some important points that I draw your attention to, which are worth being aware in the spec. The spec tells you where things will not be tested. So the Z0 and the gluon you might hear people talk of, and that's great, and we want you to be interested, but that doesn't mean you need to worry about them. You will not be tested. Okay. And again, it mentions here, we see this from earlier, about beta minus, beta plus, and so on. Okay, so we've talked about the particles that come in classes of hadrons and leptons. Well, we believe there are four force carriers that, or a number of force carriers that carry the four fundamental interactions or forces. And these force carriers we describe as bosons. That tells us something about the particles. The alternative to being a boson is a fermion, but the nature of that difference is beyond the spec. So we believe that the strong nuclear force is mediated by, that means it's carried by, the gluon. So between two quarks, we think the gluon carries it. Now between two nucleons, we discuss the pion transferring the strong nuclear force. And you've come across pions. They're mesons with zero strangeness. You don't know what strangeness is yet, but you know how much strangeness quarks have from the formula sheet. The weak force is carried by the W plus, the W minus, and the Z0's in brackets because the syllabus doesn't test it. Now, the electromagnetic is mediated by the virtual photon. So you know what photons are, and we'll discuss that word virtual at some stage in the future. And gravity by the graviton. We haven't even found gravitons yet. So how do we know which particles feel which forces? Well, all particles with mass feel gravity. So although we're not going to study gravity at this stage, that's worth knowing. All charged particles feel the electromagnetic force. So protons are repelled by other protons, but neutrons do not feel the electromagnetic force because they are uncharged. All hadrons, so pause maybe and just check back if you're not sure. Hadrons are particles made up of quarks, feel both the strong and the weak force. Whereas leptons, they are electrons, muons and neutrinos, they feel the weak force, but they don't feel the strong force. They're not affected by the strong force. In class, I'll give you some additional notes to add to this understanding. Now, we don't cover all of the bosons, sometimes called gauge bosons. You might hear that term, don't worry about it. So the ones we're going to look at in terms of mediating forces are the virtual photon, the W plus, the W minus, and they carry energy and momentum between particles. So the classic way of trying to explain this to students is to imagine two ice skaters standing opposite each other on the ice in their skating boots. If one throws a medicine ball to the other, both move backwards. So that might be a way of showing that we can transfer energy and momentum and cause particles to repel. So person A throws the medicine ball. As they throw it, they have to push it forwards, they move backwards. Person B catches the medicine ball, takes on its momentum and moves away from the person who did the throwing. We can extend the analogy. It's admittedly somewhat tenuous, but a heavy boomerang would provide a way that one skater could move towards the other. He could throw the boomerang away from him, be pushed towards the second skater, and the second skater, when catching the boomerang, having moved in a semicircle, would be pushed towards the first. So I've said beta decay is the workhorse of AS level or year 12 level physics. So let's have a good look at it. A neutron turns into a proton, releasing a beta negative and an antineutrino. So what can we tell from this? Well, the first thing is the neutron is uncharged. That tells us this is not a decay related to the electromagnetic force because the neutron doesn't feel it. Beta minus and antineutrinos are leptons. They don't feel the strong interaction. So it's not that either. And since I've just told you we don't really study gravity at year 12, then it must be a weak interaction. It must be mediated by a W plus or a W minus. So that process of elimination can be really useful, but also that takes time in an exam. So for beta decay, you must just know, because that's faster. That gives you more time to work on other things. Beta decay is a weak interaction. Well, so what, you might ask? Well, in the 50s and 60s, people started to come up with representations for these decays that they were finding. What we realized was the neutron doesn't decay directly into a beta minus and an antineutrino. If we can, in some sense, look at this, where the proton in space is produced is not the same place where the beta minus is produced. So I've got here a couple of diagrams. The top one just really shows the protons and neutrons in the equation, but then it looks at a particular neutron in the green circle. The lower one shows the paths of these particles as arrows. So one of the downs I've pulled slightly sideways, not because it moves sideways, but to show it separately, and something happens to it. It emits a W minus. Now that same diagram that you just saw on the previous page, I've redrawn here. I've not bothered with all the quarks, but you can look back and think, does that still apply to all the quarks? And it does. Okay. This is what we would call a Feynman diagram, and it's a particularly simple one, and it's really the only one we look at year 12, but we look at it in its different forms. So it was revolutionary in its time, and in class I'll talk a little bit about why, but essentially it allowed scientists to guess at possible decays by drawing diagrams out like this. From your point of view, it's a descriptive tool. It allows you to show a different representation, to think about the decay in a different and slightly more involved way. Now, at each vertex, at each corner, we must conserve all quantum properties, but the only quantum property you've done so far in any sort of detail is charge. So what conservation means is keeping the same. So the charge that comes in must be the same as the charge that goes out. So the lower vertex, a neutron flows in, no charge. And you say, well, hang on a minute, a proton flows out, that's positive. But a W minus also flows out. And therefore the proton and the W minus combined give a zero charge out. And that is how you would work out, if needed in an exam, that this decay was W minus rather than W plus. So to recap, it's not an electromagnetic interaction because the neutron. It's not a strong interaction because of the beta minus and the antineutrino. So it's weak. The weak has two possible bosons, the W plus and the W minus. You need to work out which one is involved. So you say, well, let's look at a vertex. And the only way we can balance charge at the first vertex is to have a W minus coming out. Then you look at the second vertex, which is slightly later in time, and that seems to work. A minus comes in, the neutrino is neutral, but a minus comes out. So we can decide that this must require a W minus boson simply by the conservation of charge. So I'd like you to pause the video here and draw a diagram for a beta positive decay. By all means go back. By all means look at the work so far. Maybe think about drawing it for both the quarks and for the nucleons. And think about that process that I've just gone through to decide W plus or W minus. That is almost definitely a question that will be expected in some form or other in either the multiple choice or the written questions of your exam. Okay, welcome back. Having had a go at that diagram, we need to add a new decay. So electron capture, and you'll notice they're the same particles involved. So a proton, an electron, a beta type particle, a neutron and a neutrino. Okay, but they're arranged in a different way. And you can see why it's called electron capture. The proton is grabbing an electron and turning into a neutron. But we need that neutrino that we will come back to later to explain more about why. I'd like you to pause the video here and try and write a quark equation and draw a Feynman diagram for this one. So this one, the W must travel in such a way that we capture the electron. This is a much harder Feynman diagram to draw without having seen it, so don't worry if you're not able to do that one. Okay, welcome back. So here's the quark view. We've got an up, up, down plus an electron. I hope you've added the superscripts. When typing this PowerPoint, that's somewhat time consuming, so I've missed that out here. But we can see an up plus an electron goes to a down plus a neutrino. And here we go with the Feynman diagram. So the up emits a W plus, or the proton emits a W plus. We could say either of those things, they're both true. If we take the up, because we haven't done that one together yet, it's plus 2/3 coming in, and we've got to conserve charge at this vertex here. Okay, so plus 2/3 comes in, with the down quark minus 1/3 comes out. So that's right, plus 2/3 minus 1/3, the difference is plus 1, and that plus 1 is our W plus boson coming out. But you could equally think of it as a vertex here, and therefore we got plus 1 coming in, 0 coming out for the neutron, so plus 1 has to come out for the W plus. That W plus is what actually captures the electron and turns into a neutrino. As I say, unlike the positron beta positive decay, this is much harder to get without having seen it, so don't worry if you didn't get that, but please always have a go. Moving on from the weak force then, I just want to talk briefly about the strong force. Now the strong force isn't nearly so prevalent in the Year 12 course, but it's definitely there. So Hopefully, some of you at least have wondered why the hell a nucleus sticks together. Because all you knew about until today, unless you've done some background reading, which is excellent, is that the neutrons don't do anything to each other and the protons repel each other. Nuclei should have been highly unstable and regularly falling apart, and yet they're not. Many atoms stick together and their nucleus doesn't change for hundreds of millions of years or more. So what's going on? What's holding the nucleus together? Well, it's the strong nuclear force is the force by which all nucleons attract all other nucleons. So we've mentioned the protons are repelling the other protons in a nucleus by the electromagnetic force, but the protons are attracting other protons by the strong force. The protons are also attracting other neutrons by the strong. Neutrons are attracting protons by the strong, and neutrons are attracting neutrons by the strong. Now the specification tells us that you should know about the strong nuclear force, its role in overcoming the electromagnetic force to make the nucleus stable, the fact that it's short range, so above about 3 femtometers, 4 femtometers, it really doesn't have any effect at all. Okay, but also that if the nucleons get too close together, so closer than 0.5 femtometers, the strong nuclear force is repulsive. It pushes them apart. And we can just imagine this as the nucleons butting up against each other, and so their edges are pushing each other apart. That might be a picture to have in your head of what's going on. So the best way to learn this is just by learning this sketch graph. So to be clear, a sketch graph is sketched with a ruler. The axes are labelled. Very often there are some key numbers on a sketch graph. It is not something you do freehand with a pencil, soft pencil, in a sort of sketch as we might imagine in art. Sketch graph has a very particular meaning in physics. Now this one has the red line going to 0 at 3 femtometers. I found this on the internet. More often you see them asymptotic to 0, and getting very close, somewhere between 3 and 4 femtometers. That's possibly a little bit better than this. The key point though is that in the positive range of force, we're talking about a repulsive force. So we should show the red line crossing the axis at about half a femtometer. It then comes down into a nice curve and then goes back up towards approaching 0 around 3 femtometers. That graph suitably labelled, so nuclear separation in femtometers, numbers on the axes, that shows the examiner you know everything that they mention in the specification about the strong force. Just to be really clear on these pairs, and again when you're making notes you'll have paused the video, put that graph into your notes with a big sort of highlight around it, learn this graph and the numbers on it. Well, you should also be aware of this, that what's going on, well, the protons are attracting each other by the strong interaction, repelling each other by the electromagnetic, and so on. That's worth considering. Now, what you could also put in is that the electromagnetic force is longer range than the strong. So two protons that are more than 3 femtometers apart are barely attracting each other by the strong, but they're still repelling each other by the electromagnetic. So we can think about that as we go down. Now, the final thing for today. This plot is often called, it's called an NZ plot. So we always quote the y-axis first, and I've got neutrons on the y-axis, so an NZ plot. So the straight red line is number of protons equals number of neutrons. So for example, oxygen 16 has 8 protons, 8 neutrons would fall on the red line. And then all the little black dots are stable nuclides. Okay, so for example, oxygen 16 is a stable nuclide. Uranium 238 is pretty stable. That would be on there. And what you see is for small nuclei, the stability valley, as it's often called, the white bit down the middle, is roughly along the line n equals z, or it is along that line. There are many nuclides on that line that are very stable. Calcium 40 would be another one, the 2020 dot. But as we get larger and larger number of protons, you'll see that the valley of stability drifts further and further above that n equals z line. And that's because of what we discussed on the slide previous. For the big nuclei, adding extra protons, they don't attract each other because they're too far apart. Any extra proton is more than 3 femtometers from almost all the others. But they still repel each other because the electromagnetic force has an infinite range. So in order to remain stable, we have to add more neutrons than protons as we get to bigger and bigger nuclei. Okay, and this graph is really useful because it allows us to see the patterns, and the more you can see the patterns, the less you have to learn. Right? So the green area are isotopes with too many neutrons compared to the valley of stability. And so all along the valley, if you go above, you get neutron-rich nuclei. They're very likely to decay by beta minus. All along the valley, if you get proton-rich nuclei, they're very likely, the light yellow area, to decay by beta plus. We talked in an earlier session about a small subsection of this graph and which direction things move. So beta minus turns a neutron into a proton. So the neutron number goes down by 1. If we take this one here. And the proton number goes up by 1. So a beta minus brings us diagonally towards the bottom right, and so if you're above, that brings you potentially into the valley of stability. You notice that the alpha emitters it only really occurs for very big nuclei. What does alpha do? Well, alpha takes some nucleus and it removes 2 protons and 2 neutrons. So alpha brings us diagonally towards the origin. Apologies for that arrow, it's not diagonal as I intended it to be. So this provides us with a more advanced way of trying to see why things decay. They're trying to get into that stable area where the forces in the nucleus are doing the most to hold it together. Thank you very much.